Next, we're going to introduce the main topic of this module, which is parametric curves. So basically, a parametric curve is a curve that can be described by a set of equations. So an equation that gives the x coordinate as a function of some variable along the curve, and then a second equation for the y coordinate. So essentially, we can draw a picture of this. We have the Euclidean plane like this, and then we have some curve on the plane. So a parameter is essentially an independent variable defined along some curve. So for example, we can parameterize this curve by a parameter s. Maybe we can call this point s is equal to 0, s is equal to 1, s is equal to 2, s is equal to 3, s is equal to 4, s is equal to 5, and then finally s is equal to 6. So in this context, a parameter is essentially just a variable that varies along a curve in question. So instead of, because if you think about it, even though a curve spans or it travels along the xy plane at various points, intrinsically it's only a one-dimensional entity. So it's like a piece of string that's curved and meanders along the plane. So we can basically keep track of the points along a curve with a single variable that moves along the curve itself. And that sort of variable is called a parameter. So a parameter in this context is an independent variable that describes one's position along a given curve. So just a little note, we've used the word parameter before in a different context and it meant a different thing. So in modeling problems, a parameter is essentially a constant, but we don't necessarily know what the value of the constant is. So parameters in the sense of modeling are fixed problem constants. So you might have, what's the gravitational attraction between a body of mass m, capital M, and a body of mass lowercase m? Well, capital M and lowercase m are parameters. They're fixed constants, except we haven't committed to what value of those constants has. And then we've seen other examples with parameters that were fixed constants. In this video, however, and in this module, the word parameter has a different meaning. So at first you might think that that might be confusing, having these two different meanings, but it really is clear in the context that the word is being used. So in this case, it's parametric equations, and the parameter is basically an independent variable along your curve. So here s would be a parameter, and it varies along your curve in question. So it's clear we're not doing modeling and that x and y are both functions of this parameter. So the context makes the meaning clear. So basically, given a curve gamma, so gamma would just be the curve. In other words, it's a set of points in the xy plane that consist of the curve. So given a curve gamma, a parameterization of the curve gamma is a pair of functions x equals x of s and y equals y of s for s on some interval I. So this is an interval. So in this example, it would be the interval, closed interval from 0 to 6. So it's a pair of functions, let's say, that return outputs along the curve. So in other words, when we look at the output of the function x and the function y, so we look at, for a particular value of the parameter s, we compute x of s and y of s. That point is some point along the curve gamma. So these functions basically trace out the curve as you vary s. As you vary s along the interval I, in this picture, I would be the interval from 0 to 6. You're varying points along the curve. So it's outputting the x and y values. So for example, if this is described as x of s, y of s, x of 0 would be the x coordinate of this point right here. Y of 0 would be the y coordinate of this point right here. X of 3 would be the x coordinate of that point. Y of 3 is the y coordinate of this point. X of 5 is the x coordinate here. Y of 5 is the x coordinate there, and so forth. So basically, as I vary the parameter s, which is really an independent variable along the curve, the output of these functions, x of s and y of s, taken as a pair, give me the points along the curve. So basically, a parametric equation just describes mathematically, using equations, a curve in space. Now, a quick note, there's no unique way to parameterize a curve. So one person might come along with this parameterization s, and someone else might say, well, let me use a parameter u. Maybe u is equal to 7, and then here u is equal to 8, then way over here u is equal to 9, and then at this endpoint u is equal to 10. So in that parameterization, the curve goes, u follows 7 to 10. And notice that u is still increasing as you trace out the curve, just like s was, but the numbers aren't matched up, So there's no unique way to describe the curve. Anyone can come in and come up with any way of measuring how far you are along the curve that they want. It doesn't have to be evenly spaced either. One way that, and we'll see this in Calculus 3, but one way that people often parameterize curves is parameterization with respect to arc length. That means the parameter literally indicates how far along the curve you've moved. So if this parameter s would represent, if it represents parameterization with respect to arc length, what that means is that when s is equal to 1, the distance along the curve from 0 to 1 is 1 unit. When s is equal to 2, this distance between 0 and 2 is 2 units, and so forth. That's parameterization with respect to arc length, which we won't develop yet, but it's one way that people parameterize curves. So finally, I just want to make a note that in this section, there's really two basic applications of parametric curves that we'll be discussing. So the first one, and they can be related. So the first application is just describing geometric curves. So you have some static curve in space, like this curve, and you just say, describe this curve using equations. So you're literally looking at a path or a curve. And in that sense, the parameterization really is not unique because there are an infinite number of ways to describe your position along any given trail. The second application, though, is a little bit different, and this is a trajectory. So a trajectory is just the curve in space that a body in motion follows. And when we're using parametric equations to describe trajectories, the parameter will always have a physical meaning, and that is time. So in these cases, we'll use t as the parameter, and we'll have x of t and y of t. And literally, the parameter has the meaning that when t is equal to 5, you're 5 seconds into the motion, like that. So it has a very real physical meaning, so you have something like this, and these are the notches in time. So notice that they're closer together over here. So this might be t equals 0, 1, 2, 3, 4, 5, 6. And what this would mean with this parameterization, so suppose it's a parameterization for a loop-to-loop, like a roller coaster, when these notches are closer together, you're moving more slowly, right? Because the space between each knot represents an equal amount of time. So 0, 1, 2, 3, 4, 5, 6. See what happens? 0, 1, 2, 3, 4, 5, 6. See how I had to speed up to get from 2 all the way up to 3 and then 3 back down to 4? It's because the parameterizations with respect to time. So for trajectories in space, the parameter has this very physical meaning. It's the time at which you're at the different points in space. So when there's a greater distance between equal notches of the parameter, it means you're literally tracing the curve faster. So you're moving faster along that portion of the curve. And we'll discuss that, and we'll discuss notions of velocity and acceleration shortly.